Hey, how's it going, everyone? Welcome to the stream. So last week when I was streaming, I was working on basically adding more data types to be parsed by the debugger for the variables, local variables view. So if you were watching, you saw me basically code all this up. And let me give a quick demo of what we've got so far. So actually, since last stream, I went in and just kind of spruced up the example that we were working on, just to add all the different data types that are supported now. So we've got, like, you know, char, unsigned char, int and unsigned int, long unsigned int, long int. So it's the unsigned int. And here you can see also the maximal value being written in there. So that's the max value for the signed version of the long int, which for the Vectrex will be a 16-bit value here, just like how int is strangely an 8-bit value, but that's configurable. Long ends up being 16-bit. Long is our 32-bit value. Now for this one, I couldn't actually store the 2 to the 32. 2 to the 32 minus 1. It just wouldn't let me because the compiler basically complains. I'm not quite sure why. I think it should be able to let me. Like, for instance, if I try and do this and put, let's say here, so it's the unsigned version. Where is it? Here. Like, even if I put like UL or whatever, and try to build. Yeah, so it says error, integer constant is too large for unsigned long type. So I think personally this is some kind of mistake. Maybe that, like, in this fork of GCC, when it was being modified to support the different data types, maybe somewhere in that fork, when it was setting up the value types, it didn't set it properly, because it can certainly store this value. As we can see, what I do here is I store, I basically store, this value here, the largest 16-bit value, and then I shift it left by 16 and OR in the low 16 bits. So effectively making, the largest one. So this is the same thing as if I was to just do this, right? Which is the same problem. You can see it's going to complain. It's going to say, once again, integer constant is too large for long type. But let's say I go to this example here. Whoops. If I go back to this. So here you're going to see it compiles just fine. And now let me show off actually the debugger working here. So we start launching this. I got to attach. Okay, so here we are. So here you can see all the local variables are here, and they all have basically whatever garbage values are currently, currently on the stack for those values. So if I hit F10 here, you'll see C just became 127. If I plus it, since it's signed, it's going to become minus 128. The unsigned char you see is 255. Plus goes to 0. Int I, similar, is exactly the same as char, so it goes to 127 to minus 128. Our unsigned int will go from 255 to 0. Then we've got here the 16-bit long unsigned int. So we've got 65,535 plus 1 will go to 0. And the signed version plus 1 will go to negative 32,768. And then here is what I was talking about. Now here I'm going to store, that's the max 16-bit value, but then I'm going to shift it left and OR in the other value, and sure enough, you can see that it stores this value. And yet when I try to do it on the compiler, like when I try to compile that in, it just won't let me. So not quite sure what the deal is with that, but it's all right. I don't think that there are going to be that many people trying to stuff these massive values anyway on the Vectrex. They really take a lot of room, so I'm not too worried. if somebody ever really complains, maybe I'll try and figure it out. And then here's, yeah, sorry, that was the, this was, what just happened here? Oh, this is the signed version, right? And then we basically, okay, so that's it. When we store the largest possible value, it's actually -1 here, and then it goes to 0. So yeah, basically it's what you would expect. I suppose what I should be storing there is, yeah. What should I be storing there? I guess I should go 15, like this. Or no, actually I think it's, how does it work? It's reciprocal -1, like this. Yeah, that's it. I'm just basically putting in the 2's complement to get the maximal unsigned value in here. So, just a second. Or anyway, not quite right, but whatever, close enough. So yeah, so basically all that's working. One small change I did make to the code was, first of all, I added support for char, which was really the same thing as just copy pasting the bit for uint 8t, so it's exactly the same in both. And the other thing is that originally the code did not exactly look like this. I had it like this, where I was going in my toString like this. So I was doing something like this, where I was saying display value equals, then toString, if it's signed, cast the value to int 8t, otherwise just use the value as is because it's already unsigned. But the problem with this is that toString is an overloaded function, and when a compiler is compiling this, it needs to pick which overload to use, right? So I'm actually even surprised that this compiler, I'm not quite sure what it was doing. I suppose what it's doing is it's saying what's the common type for both sides, and it would just pick one. So I suppose it was picking the unsigned type. I don't know. I'm even surprised it compiled, like I said. But anyway, what ended up happening was that only one of the 2 types would work. So I think it was signed that was working. So what I needed to do instead was, call one or the other overloads. So there's a toString for signed and a toString for unsigned. You can see that here. So here's toString for int val, and then the toString for unsigned int val. Same for long and unsigned long. So all of these types here need to have the sign checked first, and then the right overload called there. Okay, so that's great, right? I think that pretty much covers those basic integer types that we were wanting to cover here. I've got those. I've got char. The next one wants to do our float and double, so I'll take care of those now. Shouldn't be too bad. So okay, let me see here. What was I doing? So yeah, we're copying into our buffer with a loop. Yeah, I actually think I should be moving this value in. Just give me a second. All right, so I think, yeah, I guess I don't really need this in here, I'm going to move it inside. Yeah. Okay, so basically float is going to be quite similar. I do have an endianness thing. I'm going to have to like do an endianness swap depending on, or read it in a different order depending on what platform we're on. But for now, I'm going to assume little endian for, since I'm on little endian machines here. So for float, it's going to look very similar to, what is it again? Right. So it looks like float and double are pretty much the same type. They're treated as 8-byte values. That's fascinating. Okay. Also, I should do something here for the default case. Yeah, so it's going to be very, very similar. I'm going to switch on my format in here. Oh, also for char, I'm going to assert that the prim type byte size is 4. Sorry, is 1, not 4. All right. Now here, see, normally I would have had a case for 4 and a case for 8. But I guess that's not the case for us. Pun unintended. So I'm going to do that. Oh yeah, not 8. What am I doing? Format is... Sorry, it's not format I want to do. It's switch on the byte size. Yeah, that's it. Case like that, and like this. Let's copy this. Why is my format not working? So for this, I guess we'll use double V. The same old mem copy into here. And finally, display value will be, so there is no signed or unsigned, so we'll just do std to string V. So let's stick a breakpoint on this and see what happens. And let's add some float in here. Looks like the linker is complaining because I don't have the ability to add floats and multiply floats. That's a shame. So let's remove that then. So this is because basically, like when you compile a program in C or C++, part of the implementation for some of these things either come with the compiler or will be delegated to a function or functionality that's embedded in the what we call the CRT. So it's the C runtime. So these are functions that, at least for this compiler and on this target, it's expecting to find a function implemented in the CRT called add SF3, which I'm not sure what the S is for, but this would mean like add float. Again, I'm not quite sure what 3 means. Maybe it's like something related to the argument type or something. But basically, it's a function that will add 2 floats or 2 doubles, perhaps. You know. In fact, let's see. If we just do this, this should build at least. We're storing a value. Now, if I put in F, I think because they're both treated the same way. Yeah. So add SF3 comes in for just adding. Whether it's a double or float doesn't really matter. Yeah, same thing. All right, well, let's try just assigning, I guess, different values. So what is max float for, I guess in my case it would be max double. I think it's float max, sorry. FLT max. So that's float max for 32-bit. So there's double max. I'm going to assume I won't be able to enter this. Let's see. Floating constant exceeds range of double. And what if I tried to do this in my actual double? What about float max? Okay, so that actually compiled, interestingly. See, I can't even add 1 to it. Maybe if I do it this way? Okay, so that's interesting. So because the compiler can actually do this math, it allows me to do it this way. But if I tried to do f plus equals 1, it wouldn't work because this involves doing a runtime operation. Yeah, it wants to call add SF3. At some point, I'll probably implement those in assembly in my CRT so that these could be used, or at least I'll find. I think there is somebody might have implemented them already for this target. But let's just see how this behaves. So if we hit F5, attach our emulator. Okay, F10. So F, didn't hit my breakpoint. So what's going on there? Oh, okay, I know why. I did not compile correctly here. Or maybe it's because I wrote some text in there. Let's see. Oh no, okay, so then it doesn't compile. Oh, right. So declaration V hides previous. Oh, is it? What's it complaining about? This one here? Huh, I'm even surprised I was able to declare this one. Yeah, strange. going on here? Hold on. So switch on the format. These are the cases for the format. It's not making sense, is it? Okay, so for that, this here is for this if here, and this is for the switch. Okay, yeah, okay, that makes sense. Need to split these out into separate functions. For now, I'm just doing it this way, but eventually I'm going to break this out. All right. Okay, so here we go. We're being asked to, oh, so it is 4. So why did I, oh, there's float. Oh, okay, I was looking at the wrong types. Ah, that makes more sense. So float and double are actually both treated as 4-byte values. Okay, that's great. So this is actually going to fail here. Perfect. That makes way more sense. I mean, I'm going to add it just because if ever somebody implements double for this compiler, and there's no reason why they couldn't, this would work as well. Yeah, there we go. It's unfortunate that there is not like a float 4 type, you know? That's what I would use. If there was like a type or float. What does that mean? I would basically need the floating point type that is 4 bytes, you know? I'm going to put then a static assert here. It just says that size of float or size of v is equal to 4. Or is equal, I guess, to this, to the byte size. Oh no, that's not compile time. I mean, it always pretty much is, right? Like, I don't think float or double are, I think they're defined to be of a certain size, so I shouldn't really be worried. But just in case, just like how on this compiler, double is 4 bytes. Okay, F5 in here. Let's attach. Okay, so here we go. Mem copy, the display value is some massive number, which makes sense because we haven't actually assigned it yet. So let me just take off this and just see if it works. So here we've got F and D with very large values. There's 1, and there is our massive number. Huh, that's fascinating. So it doesn't do, I guess we should do this kind of formatting, because this is not, this is correct, of course. It is this value. And then we're going to add 1 to it. And then double works the same way. So okay, so that's interesting. So that means that the default for toString for floats does not actually return something that's nicely formatted. That's a bit of a shame. I would have thought that it would do this kind of thing. It's normally what debuggers do. I wonder why I can't copy the values. Strange. Convert double to string. So why is it using the double overload? V is a float. You would think that it would call the toString for floats, but it's calling the one for double, despite the fact that clearly there's a float value here. Oh, it's because it got inlined and it just casts a double. Okay, so it doesn't care. And then here it's doing a %f to get the length, 46. I thought the default %f did the thing of showing the what do you call it? The exponent format. I guess not. All right, well, I'm not going to worry about it because honestly, who's going to put huge numbers like that in floats? And if ever later on, we can always support different formatting and stuff like that. So it's just an exceptionally large value, but yeah, it totally works. Interesting. And when I pause, it comes back to main. Huh. Oh, I know why. That's funny. So yeah, I didn't even remember this because I don't think I've ever finished a main program before, but you see if you return, it loops back into main. And the reason for that is because the CRT is implemented that way. Like if we look here, let's see. Skip constructors, load current function, run iterator, call startup, jump subroutine to main. So here we jump to main, and then when we come back, we look at the return value, and if it's equal to 0, we go to restart, and then that restarts us. If it's not equal to 0, then it does what does it do? It does a clear 0xCVE. This does a cold reset, which is still the same as a restart, but at least for emulator purposes, so it doesn't really matter. Okay, so that explains why it loops back, which is kind of funny behavior. Okay, so let's so I think this is pretty good. I think this is like in a good state for me to commit it. I'm obviously going to refactor it at some point because I don't really like these kind of huge ass functions like this. But it works. And before I do refactoring, I need to see how I'm going to handle basically like types that compose types, structs, classes, unions. So when I get there, I'm going to start seeing. I have a feeling what I'll do is maybe I'll tuck this information into primitive type itself, and then I'll ask the type, hey, can you give me the display string for your current type and byte size and all that stuff? Maybe. Or maybe we'll put it away into some helper function. Right. Okay, so let's shut this off. Right, so we added the format to the primitive type. And these are all the changes we made. So we were assuming int, so we are now actually able to display different types. So put that in there. Yes, lots of changes made to the RST parser. Okay, I suppose I could keep this bit here. That's it. So display variables of type. Okay, no, sorry, let's say support displaying all primitive types, not just int. Can now correctly display char int long, float, and double, along with unsigned variants. Cool, so that's pretty awesome. All right, so we are getting to the point where I think we can start working on more complex data types. Oh no, actually pointers. Yes, that's what I need to work on next. So I don't support pointers. Pointers and references are pretty much the same thing as far as this goes. So what I'm going to do, I'm just going to keep all of this around. We're going to start simple. We're going to create an integer with a value. We're going to create a pointer, and we're going to try and change that value like this. I should just return 0 here. So this should already work. We won't be able to display P, but we should see that A will change as we step through this. So you see A is there. A's got 4. We don't have any local for P yet because we're not parsing pointers. And then you can see that A became 5. So that works. But if we look at the code that got generated now, you can see here P is of type 25 equal to *7. So this is saying P is of type 25 and it is equal, so that's interesting. So I didn't know it did the equal thing here. It's equal to a pointer of type 7. And type 7 is an integer. So we can see that up here. So here's our integer type 7. And type 25. Is there a 25? Doesn't look like it. So okay, so I guess they don't actually necessarily declare a pointer type to int here because there's no need to. Huh. That's interesting. So what if I had another pointer? I see. That's not cool. Oh, I see. Oh, I see. This is a 128 here. Okay, so this. Okay, no, that's all right. So I see what's happening here. The first time the pointer gets used, it defines a type for it. Okay, yeah. As soon as there's an equal, this will actually be a data type definition, just like up here. Because I thought it actually kept them all in one place, but it doesn't necessarily. So this is saying that P is of a new type 25. Yeah, this is kind of annoying actually. Yeah. So let's say if I split. Yeah, so I had a feeling pointers would be a bit annoying to support here. So when we see something like this, then because basically what we're saying, and I guess now I understand why 128 is used to mean two things. It's used for local variable declarations, but it's also used for data type declarations, like up here. And here we actually have a 2 for 1. Here we're saying P is a new type 25, and it is equal to a pointer of type 7, so it's a pointer of type integer. But P is a variable, you know? So whereas up here, this is the name of the data type, here this is the name of the variable. So this is extremely confusing. It's going to be fun to parse this one, isn't it? So when we see something like this, we're doing two things. We're doing a variable declaration and a type definition. I mean, I suppose we're sort of doing one, right? Yeah, we are because of the 25 here. Yeah, so we're going to have an alias or a type definition for that. Right. Oh, and let me just check one more thing. I think references work exactly the same way. So like I say, R3 is going to be equal to A here. And then R3 equals to, I don't know, 8. Sorry. R3 is equal to 8. Yeah, so that's fun. So this is actually yet another data type that got declared. Even though it is still a pointer of type 7, they gave this one a new identifier. I suppose because it's a reference. It's a bit of a shame. So if I add another reference. Yeah, so this time, yeah, so even though references and pointers are the same data type, like they're in exactly the same, they're both saying that they're a pointer to 7, it actually assigns a unique identifier for each. Another int pointer will take 25, and another reference will take 26. and then that's the offset for the local variable on the stack. So let me see if I can make this clear. So here I had this nice separation of type definition versus variable declaration. This is kind of a variable declaration and type definition, right? So let me see here. So it's a type if the Lsim match of 2 is empty. So Lsim match of 2. So actually in our case, it's going to consider this not a type. Yeah. So maybe the way I'm doing this is not quite accurate, because what I was doing is I was leaning on the idea that if there's an equal sign, that implies type definition. It's true, this is a type definition, but it's also a variable declaration. So I guess I could leave it this way, but it means having some special handling here. Wow, what a mess. Yeah, this stabs format is really crap. It's because also like my aliases here make less sense. Like I call this a type name, it's not going to be a type name, it's going to be a variable name, like it is here, var name. Maybe I'll just have another completely separate matcher for pointers. Maybe that's what I should do. Yeah, see this here? Not quite. Pointers are both type definitions and variable declarations. I'll show the example here. So it'll be like and one thing too, I think it gets more complicated with pointers to pointers. Let me see. So how do they handle this one? Let's see. Oh, maybe they do it okay. So pp is 27, which is a pointer to type 25, and then type 25 is itself a pointer of type. Okay, so it's a pointer to an integer. So it actually does it correctly. So whatever I write here should do the right thing, but I do need to keep in mind that being a pointer to something doesn't mean that the something itself is not itself a pointer. So I'm going to have to make sure that works correctly. I'm like on the fence here. What I'm on the fence about is whether I should complexify my existing regular expression to try to, tease out the fact that I matched a pointer declaration, or whether I should have a separate one just for those special cases. Okay, let me just see what happens right now, given the current state of affairs. So right now, it's going to go through all of those first, and then I'm going to get to main, A:7, then P:25. So let's see what that looks like. Oh, it doesn't say that. I'm going to need that. Okay, let me get my current line on here. So what do I got? I've got Lsim string. All right, so those are the first types. I'm just gonna go quickly through all of these. There's a lot of them. Bool. Oh yeah, I haven't done bool yet. Yeah, I gotta get to bool. All right. How many times did I hit this breakpoint? Currently 28. So if I say settings, condition, hit count is greater than or equal to 28, I think I should always get pretty much where I want. So this is A7, so this one's fine. And then here's my pointer. So if I try to regex match, it doesn't match. I'm almost wondering if I should just keep it that way. So it's not matching because after the equals, there is no star here. Yeah, I actually think that might be easier. Because otherwise, I don't know, like it's gonna get messy really fast. Okay, so let's try that. So let's say we'll call this one a local symbol pointer RE. All right, it's going to be pretty close. We're going to start with something like this. Okay, so it's always going to be the name of this variable followed by the type identifier, the type ref, really. Then it's going to have an equals star. So that's what tells us it's a pointer. And then once again, we're going to capture a number. And I think it's pretty much always like that. Yeah, looks like it is. So yeah, as you can see, this is a much simpler regular expression for us to parse out here. And let me double check this. I have that nice website I've been using. Really like this one here. I think was it ECMA? Oh, wait a minute. It's colon 25 equals, yes, asterisk. And then why didn't I catch my number here? Oh, right. I have to escape the star. That's why. Okay, so here we go. So we've got, it matches the whole thing, P25 and 7. And I need to match also the last parts of it. Oh no, those are already matched. That's true. We're just matching the inner string here, just the quoted string. This I already have. Right. So I think that's it. The first one is variable name. That's going to match the first part. The second part is our type ref. And then the third match is type definition number. This is a new type. And then this is type ref number that this is a pointer to. One thing I realize is because this compiler makes no difference between references and pointers, I won't be able to display to the user that the type that they're being shown is a reference. You know, it'll always say that it's a pointer because I cannot distinguish it from here. If I wanted to distinguish it, I'd have to like effectively parse the line where this is declared or something like that. So I think it's okay because, you know, it'll display the right information, but if ever I wanted to do expressions and stuff like that, you know, support expressions, normally with a reference you press, you know, you use a dot instead of an arrow when writing your expression, and at that point I'd need to know to validate the expression if we are looking at a pointer or a reference. this stabs outputs exactly the same info or the same output, same data for references. Cannot easily distinguish them. Maybe I'll put this note lower down. Okay, so now that we have this, what we'll do is we'll say else if we match the Lsim pointer RE here, pointer data, pointer declaration, and pointer declaration and okay, so all right, so basically we're going to take the variable name. So it's basically the same thing as I was doing here, where we match the first for the variable name, but type ref ID is the third, so that still is the same. But we also need the second one for the type definition, which is where we sort of do the same thing as here. Yeah, see, I'm glad that I separated them because it would have been really confusing otherwise. So we've got all three. So first we'll start with the declaration part, the type definition part, I mean. So we don't care about range, it will not have a range. So it's going to be very close to this here. If it's an alias for an existing type, just skip it. So that's not going to be our case here. There's no aliases here. Since no range is given, we're expected to just know the type. Yeah, so I don't have to worry about this. This has already been handled. Okay, I guess it's not the same. So what we need to do is we need to look up the type, find the type from the definition, and then create a new type that is a pointer to that one. That's what we have to do. Whoops. Right. So in our case, we're saying type not found for variable. Right, I guess we could do that. And here, what am I doing? Variable name type ref ID. My case, I guess, is type definition. I know. Getting confused here. This defines a new type. It's this one I have to look up. Right. So it is a ref I need to be looking up. Okay, good, good. So it's got pretty much the same warning as here. Which makes me feel like I should invert my find here as well. Anyway. Okay, so let's say we found our type. Now I got to create a new type. So my types right now don't have a notion of reference to. There's no such thing. I have only primitive types. So I guess I need to create a new type that is a ref or pointer to. So let's go see how we should do that. Just debug symbols. Right, so I got primitive type. So what should we call this? Reference type? Or pointer type? Indirect type? Maybe? Generic enough? I wonder if that would also work for arrays. I should try that. I wonder if arrays, well, I guess no. I guess arrays are going to be treated as containers. So some kind of aggregate. So let's call it indirect type. And an indirect type is going to have, oh yeah, that's interesting. So I can't make it point to a primitive type. It needs to point to a type, because it can be an indirect to an indirect. But the problem is that type is defined in terms of a variant of these. So I guess I could forward declare. Can I do that? I suppose I could, because yes, I suppose I could because it's a unique pointer. Oh no, it's shared pointer, right? Yeah. But how can I forward declare this if it's not really a type yet? This is starting to look more and more like I should go with a class hierarchy, because then I can make type a class. That would make it work. See, because if I want to do this, indirect type here, I won't be able to forward declare this, would I? Chicken and egg problem with variants. Excuse me. Swallowed that too fast. Yeah, can't really do this, can I? That's a shame. So I think I'm going to have to go with something like this. In any case, I am using, shared pointers everywhere for creating these, so this is not going to change much. Oh, hey, thanks for the follow, Lord Alpaca. Appreciate it. So we're going to need a virtual destructors since we have a hierarchy here. I think I can actually say default like that. And I think this is going to change just a couple of things where type was being used, but we'll let the compiler tell us about that. So if I come back here, so here I'll say create indirect type. Let me just see what the compiler says. It's going to complain somewhere where I'm using the variant. Probably in, let's see. Yeah, exactly. In my DAP debugger. So here, yeah, that's the only thing. It was nice to have a variant here so I could do some kind of runtime type information. This allowed me to effectively do my RTTI, or to do basically my virtual functions in one place, like here. So yeah, so I got the shared pointer of the type here. So if I want to do something like this, I'm going to have to do, I either have to do a dynamic cast, which I think, did I disable it? Let me see. If I can do a dynamic cast, I'll do that for now, and later on I could always do my own like RTTI or whatever, check the type and cast and all that, my own casting. But for now, I think I would be able to do it. So let's see, auto prim type is equal to dynamic cast primitive type. Oh yes, and I can't get it as a value type because that's not going to work. Shared pointer. So we're going to want to keep it as a shared pointer. So in that case, I'll do a, what is it about again? Shared dynamic cast, I think. Completely forget how to do this. I think it's like this. I'll do dynamic cast of const primitive star of var.type Wow, that actually compiled. Did not expect that to work. But I think there's a better way to do this. Dynamic cast of shared pointer. Oh, that's it. Dynamic pointer cast. That's what I was looking for. That should be better. It's going to be very similar, but it just avoids me having to do this weird get thing here. Stood dynamic pointer cast. That's the one. And I guess that returns a shared pointer, right? No, I guess it's okay. And then I can just do this. Okay, let's go for that. Great. So now we have this indirect type. So back to our RST parser. So let's create this indirect type. How was I doing it here? Ah, yes, I had an add type here, which really should be called add primitive type now that I have other kinds. In fact, I think what it is going to be a second, isn't it? Yes. So this creates an indirect type on the second. I really should add constructors to these guys. And then what else does it do? It needs to add it to my debug symbols and to this thing. So I'm going to make another function here. So this is going to be called, so let's rename add type to add primitive type. Let's add another function, add indirect type. Right, and I suppose I'm going to need more than just a type that it is indirectly pointing to, do I? No, I suppose I don't need anything. I can create its name automatically. Although maybe I should cache the name. Yeah, it could be deduced because I could just go through the type, through all types and get. But I think since, yeah, this is going to make it easier because if I ask the type for its name, and this is where we're going to start seeing maybe the virtual functions come into play because since I'm dealing with a type here, I'm going to have to ask the type for its name in order to cache it. I'm just thinking if there's going to be, yeah, there's going to be names for all the types, basically. So maybe what I'll do is, if I move name up here, yeah, I'm going to have to add constructors for sure. Okay, let's do it like this. All right, so add indirect type. What do I need? I guess I just need the type to start with. Right, so see here, I'm going to say, give me the type's name and add a star to it. And And then here I'm just going to say, do this. In fact, I'm going to move it there because we can. And finally, I need to do this here. Type ID. So I will need the type definition ID. And we're going to do this. So type def ID is the first parameter. So type def, is that the right? Yes, that's going to be the unique number that you see here, like 27. That's the type definition ID for this guy. Yes. So, okay, cool. So now we'll say add indirect type. No? It's not available? Oh, I see. Because this is in a different scope. It is indeed. Let me hoist those out because I think it's nice to be able to see them. Like that. So now add indirect type should be visible. Why isn't it visible? Oh, it is. Okay. It's just being stupid. So type def ID followed by type def ID followed by iter second. That's it. Perfect. So here we added the type. And is there anything else? Let me think. Yeah, we have to also add our variable, like we do here. Okay, so I don't have to repeat this because we've already found it. Yeah, I'm going to swap these like I said I would. So that's going to be very similar to the one. This way we could more easily refactor this code. And in fact, I'm going to add a add variable function so that I can call that in both places. So add variable so we've got name, we've got the type, and we've got the stack offset. Right. I was wondering if I should just pass in the string here. No, I'll just do it this way. It's cleaner. Okay. And then it'll look something like this, except this will already be correctly in the right format. This will be a moving name in there. This will be moving type in there. Okay, perfect. So this will be replaced with add variable, var name. In fact, I guess I could move that too. and okay. So we'll just do the same. What I like about this is that we see very clearly, I lost my stack offset here. What I like is that we see very clearly that we are doing both pointer type definition and variable declaration. We're doing add indirect type and add variable. What I'll probably do is I'll make some helpers to like look up stuff and do this kind of printf whatever. Okay, so let's build this. Make sure this builds. We're getting much closer now. Undeclared identifier. I guess I can't move it if I'm doing that. Same here, no, that's good. Wait, no, wait, what did I just do here? This is correct. That's okay, sorry, I got mixed up with types here. So this is the T that I called T here. Oh yeah, I see. I suppose I could do the same. Create our indirect type. Add it like this and add it like that. Yeah, that looks good. All right, so that built successfully, great. So what this means is that we should now be matching these pointer types. So let's put some breakpoints and see what's wrong here. Don't use move on constant. Is this a constant? Might be. Oh yeah, it is. Right. So if I don't move it, I guess I'm not really getting the advantage of moving the allocation in the string, which sucks. Maybe I'll just remove the const. Okay. Same problem here. Okay, good. So let's see if we are getting any pointer matches and what this looks like. So let's hit up with our, did I lose my, I think I lost my breakpoint from before, didn't I? Oh no, here it is. Okay, no, so I've got it here. So let's hit F5. So is this the right breakpoint? Let me see. No, this is main. All right, so this is the one that says hit count greater than 28. So what is our string? It's A7. Yeah, that's the very first. We are here right now. So that's just a normal variable match. So that goes in F5. So here's our first pointer match. Let's see if it actually goes in. It does indeed. So var name is A. That's weird. What's going on here? P25.7. Should be P. Am I just looking? Oh, I guess I'm looking at some. This is one of those. I'm looking at stale debugger data. So that's what this is. That sucks. All right, let's just look at Lsim Match here. So there we go. P25 and 7. So P25 7. That looks good. Type definition is 25 and type ref is 7. We're going to look for 7. We should find it, and we do. Got our stack offset, and now we're going to add an indirect type. .25, and here's our type. It's type integer, which is good. Create an indirect type. We're going to grab its name, which is integer, and we're going to store it int star. Very nice. And we're going to store the type that it refers to into its type pointer. And then we're going to add type ID to type. 25 points to our new type. And we're going to add it to our debug symbols. Yep, that's what we have to do. Got to add it to our debug symbols, right? And then what it's going to do is it's going to store it by name. What am I doing again in here? No, I'm just adding it to m types. What do I do with this again? Actually, I'm doing nothing with it, am I? It's okay. What matters is more that the variable name has a reference to it. So in here, we've got our name P of type. Wait, that's not right. Oh, right. Yeah, okay, so that's wrong. So add indirect type will need to return the type that we just added so that I can store it as the type here. Okay, cool. Good thing we debugged this. So return T. And you know what? I like to indicate that that's what this is going to do. So I'm going to say this returns a std shared pointer type T. See, this variable is of this type. Yeah. What I'm realizing is I'm storing all my types in my debug info, but technically speaking, I don't really need them there. All variables have a reference to them as well. But at the same time, I kind of like having all the types in one place. All right, so let's go through this again. This time we should be adding the right type for this variable. So here's our pointer again. So here's our indirect type. So this is our type star. So if we look at it, its name should be int star. There it is. and then we add this variable of that type. So there's our name, P, there's our type, and star, and there's our stack offset, and then we push it back into our variables. Perfect. So I think we're probably going to hit a few more of these. Let me just take off my things here. So here's another pointer. This is for, actually this is for our reference, which is reference 26 again. So this creates a new type, but it's just an int pointer really. And this is our pointer to pointer. So this would be interesting to see. pp27 equals star 25. So let's see what this looks like. So we certainly find it. I'm just gonna F10 over that. Let me look at my indirect type. So this will be interesting to see. So if I say indirect type, pointer, name, and there's int star star. So this is good. So okay, so that means that we are now supposedly parsing pointers and references correctly. The other side of this equation, of course, is to be able to display it in the debugger, right? So if we go back to our debugger here, here's where we did our little dynamic pointer cast. We're going to want to do another dynamic pointer cast to grab our indirect type. But now the thing is that all of this all of a sudden needs to become recursive, because we're going to want to travel through our indirect types until we get to the actual type to get its value, I suppose. Or maybe not. Probably what we want to do is, if it's a indirect type, we just want to display an address maybe. Although it is nice when the debugger also displays its dereferenced value. But technically speaking, we should be able to expand our variable and then see what it refers to. Yeah. We can take a look again at how this guy works. That's it. If the value has structured, if the value is structured, has children. I guess that's more for structs and all that. But I suppose we could consider it having a child, yeah. If the number of named or indexed children is large, number should be returned via the optional named variables and indexed variables. Yeah. Yeah, so that's it. There's this variables reference thing that we can use. Sorry, I saw memory reference here. So this looks like it's for function pointers though. Okay, so forget that. Yeah, I think what we're going to want to do is set a variable reference here. But the question is to what? Because here the variable reference that we were setting was the stack frame, if I recall. Right, this is a different variables reference. This is the one on a variable that we create. So here, what we could do, but it is an integer, that's the only thing. So I don't have a easy way to get back to it. I'm gonna have to start creating like some kind of ID system, I think. Okay, let me just just try this. So the display type is clearly going to be the name of the type, so that's pretty easy. So it would be more like this. Now, as for the display value, I guess if I'm going to display an address, at least for now, it'll be something like this, right? I already have the variable address here. Okay, so let's just say we start with this, assuming this compiles. At the very least, we should see our indirect types in the debugger. So let's see. Do that, attach. Oh yeah, hit some breakpoints here, take those off. Okay. So there we go, bunch of references, and these actually do look correct. These would be the stack relative offsets that we would get for these. Yeah, basically. Oh, how come A is not showing its value anymore? I must have broken something here. Let's take a look. A is here, shared pointer, name is int. Why am I not seeing the type correctly here? It should be primitive type. But I'm not seeing primitive type. It's only creating a base type here. Normally the debugger is able to show this correctly, but it's not seeing its type. I must have messed this up. Let me see. I must be slicing. Somewhere I'm copying type for sure. Let me see here. Probably when I create. Let's see. Here. Yeah, okay, that's the problem. We need to be, just like for indirect type, I need to be making my type right off the bat here. So this should be auto pt equals to stud make shared of primitive type. Yeah, so I was slicing it because I was using a variant before. Okay, so we make it like this. We initialize it. What's the problem? Okay, it's good. We don't need this anymore. And just for symmetry, I'll return it as well, even though we don't need it right now, but just in case. All right, fix that. What's up with this printf here? Oh man, my back. Okay, so we've got our primitive type back. There it is, primitive type. So that's what I was expecting to see. So there's A, and it's got 4. Now it's got 5, 6, 8, 10, 12. All right, looks good. So yeah, so now back to this problem of trying to display a pointer and being able to expand its value and actually show you its value. So there's basically two ways to do this. What I have right now makes it so that I can either, there's like basically two strategies here. I can try to just show the value that our pointer points to. Now the question is, if it's a pointer to pointer to pointer, do I show, do I travel across all those pointers to show the final resulting value? Maybe. The other thing I can do is add a child variable so that you go ahead and you expand it, in which case there'll be another call and it'll actually fall through here, I believe. Because, will it fall through here? Yeah, it will. It's because it's going to go through variables here. Will it? I'm not sure. If I add a variable's reference here, it'll do another variable's request with that variable's reference, which is what we're doing here. And right now I'm assuming that the variable's reference is a call stack index. So definitely I'm going to have to change that if I go down that route. Anyways, I already planned to do that. This isn't the best way, assuming that variable's reference is always a call stack and index. So say it's not a call stack index. Say it's actually it's a custom variable reference. What would it refer to in my case? Because I don't actually have a variable for it. Yes, a pointer does point to an actual variable, but we don't have that information. All we know is its type, and we know the location of it on the stack. Like here, P2, no, sorry, P. So we've got A, where's my P? Oh, I deleted it. So P, which is type 25, is a *7, but we don't know that P points to A. You know what I mean? Because it's just a pointer. And you know, the fact that it happens to point to A is a detail. So what I'm supposed to do with this is I'm supposed to interpret the data that is there at the address. So I know it's an int pointer, so I need to dereference it. So I need to grab the address that's there and treat it like an integer star and dereference it. Yes. Thinking how I'm going to do this. I mean, basically it's the same thing as this. I think it is going to be just to recurse. Ultimately, it's all about this variable address here. Here I'm getting the variable address by doing stack address plus stack offset. What I should do is hoist this out into a function that I can call with a variable address, and then I can just pass in the variable, actually what I'm displaying here is not right. I'm displaying the variable address of my pointer, but really what I want to be displaying is here. This is not right. I wanted to be displaying the value that my pointer is holding. So I need to dereference this guy, get the address there, and that's what I want to be displaying. That's right. That's right. Okay. This is starting to come together now. Okay, let's start with that. So to do that, I'm just going to have to read twice from the memory bus. I really should add a function. Did I add one for 2 reads? I don't think. Oh yeah, I did. Read 16. Perfect. That's what I'm going to use. That should return to me what I should be displaying. like that name. And see then here to do, what we're going to do is we're going to say read value at read and display value at value address. Now, with this, what we should see is that all of those references in my examples, all of these basically should have the same address as the address of A. We saw before what we were displaying was the address of each pointer on the stack, which isn't really that interesting. What we should be seeing is that all of these refer to the same thing. So let's see, is built? Yep. So let's see that that's working. So we'll bring this up. And it's not at all what I was expecting to see. What did I... Oh, is it because they're not initial? No. Oh yeah, maybe it's because they're not initialized. Yes, that's right. Actually, it makes perfect sense. So now, supposedly this is the address of A. And let's see here, P2 gets the same address. And that one gets the same address. That guy gets the same address. See, this is starting to make more sense. And see, this is a pointer to a pointer. And here we can see it's at DD, which is actually before DF, which makes sense because our stack is grows in the negative order, like it gets smaller basically as we push values on the stack. So, and this here would be 2 bytes away, which also makes sense because it's a pointer and pointers are 2 bytes on this architecture. So there's D and DE that contain the address, and it's the value it'll point to is basically this, and then of course that'll change that to 12. So this is good. So now what I should do is I should take this out, like I said, and make a recursive function that will basically travel down the data type and show us the value there. I think I'll make that a separate change. I think for now, just the fact that we can display pointers and references, the way that we're... Hey, what's up everyone? I am not sure if this is working. I got completely disconnected here. Just wait. Okay, I think I'm back now. Yeah, sorry about that. I don't know what happened. My internet just dropped. So I'll probably have now 2 videos. But anyway, such is life. Okay, so yes, where was I? I was going to try to get this thing committed. Really odd how my connection just dropped that way. Oh well. Okay, there we go. Okay, so what I got here, this, and this. We want that. Direct type. Lots of RST parser changes here. I think that's it. Support displaying pointer reference values. Support displaying pointers just pointed to address. pointers and references are now parsed, and the pointed to address is displayed. I'm tempted to do this right now, but I'm feeling like it is 11:15. I don't know if my internet's going to drop again, so maybe it's a good time for me to stop. Anyways, I'll be back in a couple days on Thursday night, where we will continue on this pointer thing, and we'll get it to display values correctly. And so we'll see how that goes. So yeah, thanks for watching, and I'll catch you next time.